Yeah. So, hello students. So let's continue the discussion on the different connecting devices, right? I hope you recall that last class we looked at a couple of devices, but we said that these devices are only confined to do some layer functionality. So we saw repeater, right, and active hub, and both these devices I told you these are layer one devices, right? Which means it's confined to do only the physical layer functionality, where what is its role as a device? It's not doing much intelligent decision making. It is just going to receive a frame, regenerate the signal, and then forward it, right? That is all it is going to do. So basically, we said repeater can extend the range of a particular LAN, right? When you boost its signal strength, right? So that's what a repeater is bounded to do. But then we understood that active hub is basically, much more sophisticated than not just doing, receiving from one, port and forwarding, but it's basically a multi-port repeater, right? So when active hub came in, people started to build star topology and connect multiple devices. But as such, it is only doing the regeneration functionality, right? When the frame is received through one of the IO port, it is going to regenerate the signal. But this time, what is it going to do is it is going to forward it through every other outgoing port except from the IO port from where it came in. So which means wherever the destination is connected to, it is going to be connected to any one of the IO port, it is going to receive it. So that is where the intention with where the active hub came in. But active hub cannot do decision making of, okay, now, look at the frame, make a decision which IO port to forward. All this it cannot do because it's confined to do only the layer one functionality, right? So it is typically flooding. So I'm using this word called flooding, right? So if it is receiving frame in one of the IO port, the active hub is basically going to do forwarding through how many other port is going to send it across all the ports, right? So that is all it is basically confined to do. But then if you have a connecting device which can make an intelligent decision looking at the frame, right? Looking at the header in the frame and then making a choice, right? Making a decision which port to forward to, which IO port to forward to. Now that is where the intelligence comes in. So we are going to now discuss today on bridges, right, as well as switches, right? Both these are layer 2 device, right? So if I have to say bridge and switch are both basically doing the same, but then in terms of the technological advancement, you need to understand that bridges are now being replaced by switches, right? So switch as a device is now capable of doing very high speed switching. So that is the advancement in technology that we need to understand. But in terms of the functionality wise, both bridge and switch are typically the same. It's doing the layer 2 functionality. So when I say it's a layer 2 device, you guys should not forget that it is doing even the layer 1 functionality. Without the layer 1, nothing can be done, right? So it's going to regenerate the signal it receives as a layer 1 functionality, the 5-layer functionality. But in addition, what is that layer 2 is? Layer 2 is a data link layer, right? It is going to look at the header in the frame. So when you receive a frame, right, it's going to look at the header in the frame. What is there in the header in the frame? You have the source MAC address and you have the destination MAC address, right? So when the bridge receives a frame in one of the IO ports, right, it is going to look at the header in the frame and make a decision, right, whether I need to forward this frame, right, or I need to drop this frame. So forward or drop. Now this decision, right, it is going to make. If I need to forward, right, which port to forward, that decision making also a bridge can do, a switch can do, right? So it's going to tell in which IO port it is going to forward in case it needs to forward. In case it's saying that, oh, come on here, we are not going to forward this frame. That decision making can also be done, which is basically called as a filtering capability. So how does this intelligence comes in? Right? By looking at the header and the frame and telling, hey, come on, you forward it through the third IO port or the fourth IO port or whatever be the IO port number, right? How does this intelligence comes in is by having a database. So at layer 2, the bridge or the switch is basically going to maintain a database or a table. That database is called as a forwarding database, right? Or forwarding table, right? Whichever you want to call it. So what is this table or database going to contain? It is basically going to contain two columns. I'll just make it very simple. It's just going to maintain two columns, right? So it is going to maintain all the list of MAC addresses, right? Because we are now dealing with layer 2, right? When we are dealing with layer 2, it's all about the hardware address, right? So whatever devices, end devices that are connected to the bridge, so the central device is the bridge. So all the devices MAC address is going to be listed here, right? And every port in the bridge is going to have a port number, the IO port number. So which MAC address is mapped to which port number, right? So that detail is going to be entered here, right? So you're going to have a database which is going to have the list of all the MAC addresses and the port in which those devices are mapped. This is the thing that's going to happen. So when I say the bridge can make an intelligent decision making, what is it going to do is when it receives a frame, it is going to look at in the table and perform a table lookup mechanism. So we will look at this with an example so that you understand this with clarity. And based on the information that's there in the database, it's going to make an appropriate decision, right? Which port to forward, whether it needs to forward or which port to forward, right? If it's forwarding. So having said this is the main thing that's the bridge as at the layer 2 is going to do, right? But then there are two types of bridges. One is called transparent bridges. And the other type of bridge is called the source routing bridges. Transparent bridges was basically used in the Ethernet LANs, right? Which was very successful. Source routing bridges was basically used in token ring relance, which was quite obsolete, and this bridges really wasn't very successful. But we'll try to understand the difference between the operation of the bridges, compare with these two types. So let's now take up the example so that we can understand how bridge works and how does this table really, who's putting all these entries in the table? Is there any algorithm to do that? All we will try to understand. So bridge has a forwarding table. Now that's the very important point, right? And that table is only used to make all these decisions. Now whether to filter a frame or to forward a frame, right? So without this table, the intelligence doesn't comes in. Okay. So having said, now let's look at a particular case where you have two LANs that you see, right? Two LANs are of the same protocol, say Ethernet LAN, right? Now you're connecting these two LANs via a bridge. Okay. Now, if you look at in LAN 1, right, it's all these LAN 1, LAN 2 you see is like a typical bus topology, right? What will be the topology that you see? Now, these LAN 1 has two devices, two end systems, and the MAC address of these systems are shown here. Okay, typically in LAN 2 also you see two devices and the MAC addresses are shown here. You know the MAC address is basically a 48-bit address, and how many hexadecimal digits it is needed? I hope you know this calculation, right? So 6 bytes are being represented and each byte has 2 hexadecimal. Okay, so for the ease of discussion, let's now take the last byte alone instead of looking at it because it will be much more easier to deal with that. So 41, 42 hardware addresses are in LAN 1 and 12 and 13 hardware addresses are in LAN 2, right? But then bridge, you see in this typical example, bridge is only having two IO ports in this bridge. But typically a bridge has more IO ports. In this particular example, you see that the bridge has two IO ports that are mapped to it. Now, when any device, right, wants to, communicate or transfer messages to any other device, whether two devices in the LAN 1 itself want to communicate or from LAN 1 to LAN 2 to communicate, we will see how the bridge works. For this, I told you the bridge is going to maintain a forwarding database or table in the layer 2. So if you look at, we will see a table, the database that is already having information, right? And then take up this example. So if you look at in this, in the port 1, right, of the bridge, what are all the MAC addresses that are mapped to the port 1, right? These two devices are connected via the port 1, right? So 41 and 42, you have two entries in the table, which are mapped to the port 1 of the bridge, right? Now, typically you look at this 12 and 13 MAC addresses are mapped to the port 2. So you have the next two entries where it is being mapped to port 2, right? So now let's look at how it works, right? So you have now the table already populated, which has all the list of MAC address in which port of bridge it is mapped to. So whenever bridge receives any frame, it can look at the table and make a decision, Now let's look at the first example. Now say system, with MAC address 41 wants to communicate to the system with MAC address 13. Right. So when system 41 generates a frame, it's going to add in the frame header the 48-bit address. So let me just put the last byte alone. So 48 is the source MAC address, right? And the destination MAC address is going to be 13, and you have the data unit that you got in the trailer that you generated. So when this frame is put on the LAN 1, right, since it's basically a broadcast medium, right? So every device is going to receive that, and the bridge is also going to receive this frame via port 1. So when the bridge receives the frame, it is not just going to do the regeneration functionality as you're aware of, it is also going to inspect the header in the frame, right? And so when the bridge looks at the frame, it goes on to find, okay, now this is coming from the source address 41, right? But the destination that it is mapped to is 13. So where is 13? Now that's the next question. So it goes and looks at the table, right, and scans through every entry. And so you see that 13, okay, it does not match with the first entry, does not match with the second entry, it's not match with the third entry, but matches with the fourth entry, and it finds it is mapped to port 2. So what is it going to do now? It's going to make the decision of forwarding that frame via the port 2. Right. So when it forwards the frame, it is the physical layer is going to regenerate the signal and forward it through this. And the frame is now transmitted over the LAN 2, and every device in the LAN 2 is going to receive it. Obviously, the others are going to discard. 13 is going to receive it, right? So the bridge basically made a decision making looking at the table, right? Finding out the corresponding match in the destination address in which port it is mapped to, and it forwards the frame after regenerating. So this is what typically a bridge does. But when will the case where the bridge is basically going to drop the frame, right? So that is the next question, right? We say it has a filtering capability. So what is the benefit of filtering capability? Is bridge is not going to forward the frame. When does the situation happens? Let's take the example 2. Suppose say 41 wants to send message to 42, which means devices in the LAN 1 wants to communicate, right? So when 41 sends a frame which is destined to 42, right, and it's transmitted over the LAN 1, every device is going to receive in LAN 1 and 42 is going to receive it, right? The traffic is okay, confined here, but then the bridge is also going to receive it via port 1 where it says, this frame has been destined to 42. Now bridge goes on and scans the table and finds that 42 is mapped to port 1 only. I received this frame through port 1 and the destination is also mapped to port 1. So I don't need to basically forward this frame, right? If I forward the frame, unnecessarily I'm going to create a traffic in LAN 2, right? Which is only going to basically reduce my throughput, right? When it comes to the LAN performance as such, you're not unnecessarily going to create traffic in LAN 2, which could be avoided here because it's a communication that's happening in the LAN 1. You don't need to unnecessarily go and, create traffic in LAN 2, right? So bridge is basically going to divide that and then ensure that, you unnecessarily don't crowd the traffic, in another LAN where it is not destined to. So that's where it filters, right? Or it drops the frame by not forwarding it to the other LANs or other outgoing ports, right? So this is the idea where the bridge, has this intelligence to do switching of the frames, right, to the respective IO port, and it is not possible without this database. So the question now that I would like to, you guys to ask is, come on, we now need a case where this entire table, right, information, the database needs to be populated. Now, without this information, the bridge cannot do this intelligent switching process, right? So the question comes here, right? So who is basically going to feed all these entries in the table, right? And so there are two solutions for this. So let's look at both the solutions. One solution is to manually feed all the entries, right? In this case, you're only seeing 4 systems, right? But then if you have a bigger LAN with so many devices, hardware addresses connected, right? And you have to maintain a big database of all this, we are going to face challenges, right? So we will understand what's the challenges that we have if you're feeding the entries manually. But then if you have an algorithm, right, which can automatically learn, right, and update and make entries in the database, right? That is where we can say it's completely a dynamic approach, right? So we don't want a static approach, right, where we feed the entries manually, but we wanted to prefer to a algorithm which is going to be very dynamic, which can automatically make the changes, add entries and all that in the table and populate the database, right? So we're going to understand both these together. So let me, before we get on to such things, we will try to take up some points here. The very important point here is this: Bridge is not going to go and change the frame header. Bridge is only going to inspect the frame header and make decisions, right? So having said that, connecting device is only going to look at the header, look at what is the source address, what's the destination address, look at in its table and make appropriate decisions, right? It is not going to go and change the physical address in the frame. The router can do that. The higher layer devices, the much more intelligent devices like router can do that, but bridge is only basically going to look at what is there in the header, right, and look at the address, MAC address, and then make decisions. That is all it is. Okay, so having said, we'll now go and start focusing on the first type of bridge, transparent bridge in our discussion, right, and then try to understand how this table is getting populated dynamically and all that, and some algorithms related to that. So the type of bridge called transparent bridge. Why the word transparent came in? Right now, if you look at transparent, the word here is the end systems or the stations which are connected to the bridge, right? They are completely unaware that we are actually connected to the bridge, because the end station does not need to do any configuration, right? I am connected to this bridge and so on. So what should the configuration that I need to do to connect to that bridge? All that is unnecessary, right? So having said that, transparent bridges is going to make the end devices job even more simpler, because you want to create a LAN, you connect them to the bridge, right, and the bridge will take care of forwarding it, right? The end stations need not break their head. But when you look at the other type of bridge called source routing, it's quite challenging because the end systems or the stations have to do break their head to find out which route to do. So there's a lot of work the end station has to do. But here in transparent bridges, the stations are completely unaware of the existence of the bridge itself. That's why it's called transparent bridges. But whatever it is, with the bridges, if you look at the operation of the bridge, the IEEE standard has basically specified certain, guidelines that the bridge needs to comply to these rules. So what is that IEEE standard that comes in? IEEE 802.1, once basically standardizing for the bridges comes in, and it's 1Q. Okay, you don't need to mug this, but just be aware that IEEE 802.1Q 1D, I'm sorry, 1D goes on to specify certain rules that the bridge has to do. The first thing is this: when the bridge receives a frame, right, its typical task is to forward the frame from one station to another, right? So that it has to do. The second thing is, the IEEE 802.1D standard specifies this. Come on here, you have the forwarding table, right? You don't manually feed it, but automatically start to populate the entries in the table. And how are you going to automatically start learning is only when you start receiving frames, when you start moving frames from one station to another. So when you start receiving frames, you're going to forward the frames. You are going to automatically learn by the frame movements that's happening in the network and feed your forwarding table. So this we will understand by the next example of how this specification is basically being implemented, right? And the third important point here is there is going to be a problem that can happen, which is called the loops, right? So the IEEE 802.1D spec says the loops should be prevented, right? So how are you going to prevent that loops? We are going to understand where these bridges are going to implement an algorithm called spanning tree algorithm. So the focus of this lecture is going to be understanding how these IEEE 802.1D specifications is basically being implemented, right? And how these problems of loops are getting resolved. How is the learning process happening? All this is going to be the focus of this. So when it comes to the learning process, obviously the question now is you have the forwarding table, the bridge is having the forwarding table, right? And it's going to have the list of all the MAC addresses and the ports in which it is mapped to, correct? So feeding all these entries manually, right, the network administrator does, then it's called as a static entry. So static entry meaning someone goes and manually enters the information in the table. But this is going to be a problem, right? If you, it's not going to be really dynamic. For example, if you want to say in my lab, right, we have in our advanced network lab, I want to increase the capacity of the lab by I want to add 50 more systems, right? Then I'll have to go again to this bridge table and add all the 50 MAC addresses that are mapped to the specific ports of the bridge, right, in the table. And this is again a manual procedure. The second thing is, suppose say some of the network adapters or the hardwares are not functioning, right? I'll have to go and change all the network adapters in those devices. Then I'll have to come to the table and change all the MAC addresses or update the MAC addresses that are mapped to that respective port. Again, a manual work, right? So like that, if there is any change or additions or deletions that's happening, right, the lot of manual and work goes on in going and updating and making these entries in the table. So we don't want that kind of a static process. Rather, we want a algorithm, right, which can automatically populate, right, and update the database. That is what we're going to look at, and that sort of a table is called as a dynamic table. Okay, so focusing on this approach of how this learning process happens, I'm going to basically take an example. So I want you guys to carefully look at this picture and now make your analysis. So how many LANs you see here? All these LANs are of the same protocol, right? So you see 3 LANs, right? And these 3 LANs are typically like in a bus topology. And the bridge, you see that how many IO ports are there in the bridge, right? You have 3 IO ports. So now, how does this learning process happens? We are going to look at from the scratch, right? So when initially the bridge is going to have an empty database, empty forwarding table. It is going to be like a dumb device now, right? So that interesting thing we will start to look at. So the intelligence start to slowly start coming in only when the traffic, is generated in the LAN, right? Only when there is frame movements happening in the LAN. Then only the bridge will start to gradually learn and start to become intelligent. So we all build our intelligence only through learning, right? And then we build our intelligence. So same way, the bridge is actually going to, make itself intelligence by learning, what's happening in the entire LAN, right? So we'll look at this. So initially, the bridge forwarding table is empty. Okay, but now as devices starts generating frames, right, we will look at how it works. So now let's look at the first case. Now suppose station A, right, in LAN 1 wants to send a frame to station D in LAN 2. Right, so it is so ideally now let's look at this. All these letters that you see are the MAC addresses. Okay, so just for the simplification, you know that forwarding table is only going to contain MAC addresses and the port number, right? So now when initially A wants to send a frame to D, it is going to put in the header, right? Source address is A, right, and destination address is D. So when it is transmitted over LAN 1, right, it's a broadcast medium in this case. So when the frame is transmitted, it is going to be received by the bridge via the port 1. So the port 1, bridge is going to now inspect the frame header. It understands that, okay, I'm receiving a frame now. The source address is A and the destination address is D. There are two things the bridge is going to learn from this, right? So one is, its table is empty, right? But then what it can do now is it does not know where D is, right? But it can now learn one thing. What is that it can learn now? Hey, come on here. I am receiving this frame and the source is A, right? I am receiving this frame via port 1. So the first thing that it is learning is, okay, I've received a frame through port 1 and the source address is A. So A should basically be mapped to port 1. So that it makes an entry, right, by this first frame movement that happened where it understood from where the port came in and who sent this frame. And so it made an entry. But then it looks at the destination address D and there is no information about D. So it does not know where to forward it to. So you know what is bridge going to do? It does not have the intelligence, right? It will now become like a dumb device. It will become like an active hub. What is an active hub going to do in such cases? Active hub is basically going to regenerate and flood it through all other IO ports except from where it received it through. So it does not know where D is. So what did it do? It is basically going to flood the frame by forwarding the frame in all the outgoing ports 2 and 3 except 1. Right. So obviously, you know that LAN 2 and LAN 3 is going to receive, which is actually not very good in this case because it's basically creating traffic in all the LANs. But what has happened now is, it was able to forward the frame and LAN 2, D has received it, rest all are going to discard it. But then it gradually starts to learn, right? It needs that intelligence to start building it. So the first step is to learn through this. So it still does not know where D is. Right. So it was typically doing the active hub functionality. But what it has learned from this frame movement, it has learned that, okay, A is mapped to port 1. That is the first intelligence. So when every device starts to, generate frames and all that, at one point, it will fully learn and, keep its table ready. Right. So let's look at another scenario now. So A has sent a frame to D. D has received it. Now let's look at another case. Suppose E wants to send a frame to A. Right. So in that case, what's going to happen now? E is going to put in its header, right? Source address as E and the destination address is A, and it's going to place on the LAN 3. And bridge is going to receive this frame via the port 3. So what is it first going to do? Okay, it now learns that frame E has sent it, right? And it is mapped to port 3. So let me put an entry that E is mapped to port 3. But next, this frame has to be forwarded to A. So now bridge goes and inspects in the entry. So it goes and finds that A is mapped to port 1. So now bridge has the intelligence, right? This time it is not going to do the flooding like the active hub, right? It is basically going to regenerate and forward it in the port 1 alone. So it was able to make the decision of which port to forward, right? This happened because of the gradual frame movements, right? Now let's look at the third case. Now B wants to send a frame to C, right? The third case. So in that case, what's going to happen? B is basically going to, right, put its header source address as B and the destination MAC address as C. So when the bridge receives the frame, where is it going to receive? It's going to receive via the port 1, right? So when it receives via the port 1, it learns that B is mapped to 1, but it does not know where C is. So what is it going to do this time? It's going to behave like an active hub, right? It's basically going to flood the frames across all the outgoing ports except the incoming port. So anyway, C is going to receive that. But then if C starts to send back a response to B, right? Now this time it learned that C is basically mapped to port 2 and it's not going to flood, and it also knows that B is mapped to port 1. So it switches and to the respective IO port 1. So what happens is when, slowly, right, it starts to learn from the frame movements that's happening, gradually it starts to populate its forwarding table. This is the learning process. So the learning process is dynamic, right? And it keeps updating its table. I hope you're able to understand the learning process that's happening. Quite interesting in terms of this. It's very dynamic, right? Even, to ensure that if a station is moved from one LAN to another LAN, the forwarding table can still be, updated. So what happens is that there is an additional, column that you maintain in the table, right? Which is basically a timer, right? So every entry in this back table is going to have a timer value because you need to keep updating the entries, right? And to ensure that it is refreshed periodically and you have the latest information, there is going to be a validity for every entry. So the validity says for 5 minutes, right? If you're not receiving any further updates after 5 minutes, so you will basically delete that entry, right? So it becomes outdated. But then within that 5 minutes or beyond that, if A is again sending its frame, right? It's basically going to go and update that timer and increase the validity of that particular timer. So like this, when you have timer associated, you're only maintaining all the updated entries, right? You're keeping refreshing your entries, right? By having the updated information. So in case if A is moved from LAN 1 to LAN 3, right? And the timer is entry is basically going to be expired. So then obviously this entry will be deleted. But then if A from LAN 3 now that is moved, right? Say A is now here in LAN 3, it is going to now generate a frame freshly, right? To some other stations. Then you obviously will add another entry this time where A is mapped to 3. So even if the station is moved from one LAN to another LAN, if the MAC address are changed, all these are going to be dynamically updated in your learning, forwarding table. So this learning process is completely dynamic, and it only happens gradually through the frame movements that's happening in the network. I hope you're able to appreciate how the learning process happens, right? So having said, we'll take a short break, right? And we'll see in the part 2 of the video.